So, we are continuing our discussion on software defined radio architectures. We have seen that we have two types of architectures, homodyne and heterodyne, and the others are their combinations. Now, we will look into the limitations of transmitter receiver front ends, and for these different architecture how they what they implicate. So, first is allo leakage. As you know that in homodyne structure we have signal at RF and the allo frequency is equal to the RF frequency. In heterodyne structure we can choose our RF frequency separate from the RF frequency. So, what is allo leakage? Basically when we are putting our signal in the quadrature phase by using a allo, then some of the allo might directly leak into the direct path. So, what will happen in the case of homodyne? Our signal which is being modulated by this allo one is a broadband signal. It has some bandwidth. So, let us see in the frequency domain. This is our RF signal, which is a broadband signal based on our chosen signal. It can be any OFDM based signal, it can be WCDMA, WiMAX, LT, any of those signals, and it is a band limited signal, it is RF signal at the FRF. But our allo is basically a sinusoid, it is a oscillator. So, it will have the leakage from there which will be like this, and it will be hiding under this FRF, because FRF is equal to FLO. So, it will create a distortion. Basically it is frequency domain, and it was signal dBm per hertz, basically PSD, power spectral density. If I am showing it here in the time domain, if I try to plot our signal and suppose our signal was supposed to look like this, okay, because now we have a hidden component here of this sinusoidal. This signal will not be like this, it will be something different depending on our new sine signal. So, of course, it has been distorted now. So, this distorted signal, it is amplitude. When received by a receiver, the allo component cannot be separated and it will be distorted signal. Now, in the heterodyne case, if you see here, this allo is leaking here in the both paths because of both the allos. This is IF allo and it is the eventual allo which is bringing our signal to the RF frequency. And we have two frequencies here which are oscillator frequencies, they will be single carriers, and our original signal, the RF signal, which will have the frequency of FLO1 plus FLO2. So, how that will look like? Homodyne architecture and it is heterodyne architecture. So, our signal which was the RF signal FRF, it is FLO1 plus FLO2. Now, FLO1 is a signal which is here, and FLO2 is another signal, oscillator single carrier signal which is FLO2, but they are at different frequency from the RF signal. So, basically in the receiver side the band pass filters will be able to to separate it properly. So, in the heterodyne we are able to keep our signal intact and we will have our original waveform shape in the time domain. So, let us write it completely, PSD dBm per hertz. Okay. So, allo leakage is more prominent in the homodyne structure as compared to the heterodyne structure. Now, look at the DC offset. Actually, DC offset is again after effect of having the allo leakage. Now, allo is leaking from this part to the previous to the mixing path. So, as you can see, we had these mixers here which were allowing us to multiply our sine signal to this our cosine signal to this in phase component and our sine signal to this out of phase component, right. So, this was supposed to be our signal, but now because our LO is going before this mixing signal, what will happen? It is also entering from there. So, we will have a DC offset because this mixer will do what? So, we are having mixing before our quadrature mixer. So, mixer is having LO, FLO, and this FLO is leaking here. So, it is also having an FLO apart from other components which is I phase of the signal. So, this will have the component is FLO plus FLO, which is 2FLO. It does not matter because of a band pass filter which is here, it will remove this component. But what about the FLO minus FLO component? It will be at DC. So, it will be appearing at DC and will not be taken out by our BPF, and that is why its name is DC offset. So, how our frequency domain signal will look like? Power spectrum density dB per hertz, if you see, we have a signal appearing here apart from FRF signal, which is the actual signal here, right. So, this is what we call DC offset. Because of this component, the amplitude level of all the signals goes high. Now, what will happen in the heterodyne case? Again, self mixing is there, right. So, because that self mixing, this DC component was there at this instance, because this band pass filter, it was this is allowing this signal to go through, but the DC is also creeping, which is bringing the amplitude up. Now, because of the LO2, because we have two stages here, after LO1 conversion, right. So, after LO1 we have FIF, and then we were having this DC component there. After LO2 second conversion, our signal is at FRF, right, and this FIF will appear here and this signal will be here at the RF frequency, right, because it was 0 before, now it is up converted to new signal. So, this FRF will be what? FLO 1 plus FLO 2, as we discussed earlier, this one, and this will be FLO 2, which is this plus FLO 2, right. So, this component will be there. So, this DC error we cannot avoid. Once our signal will be taken down, we can filter it like that. But if our filter is not sharp and it is, we do not have components like capacitor to stop it, then this will appear there. So, now there are two types of DC errors. One is caused by LO leakage, self mixing, as I have shown in this example. Another one is dynamic DC errors. It happens when some incoming signal is coming and suddenly its amplitude changes, but our automatic gain controller in the receiver, it is not able to follow it properly and it stops suddenly. So, there is a jump in the amplitude, and that also brings the DC error. It is called dynamic DC error. So, what is the effect of this DC offset? In the LO we can see the distortion was there. Because of the DC offset, in the constellation diagram we can see that the constellation shifts in one direction, and it shifts in the direction where actually our amplitude is being added. So, in this constellation diagram which I am showing for the 64 QAM, we can see that the bits are shifted towards Q. Everything is every point has a addition of some amplitude in the Q direction. So, this is the DC offset was coming on the Q side then in this case. What will happen because of this? The symbols will be misdetected, because earlier what it wanted to when it wanted to read this symbol, that symbol is now here. So, instead it will read this symbol and interpret that this symbol is basically this symbol, which is wrong information. So, accordingly the bits will be converted back in a wrong sequence, and your BER will be very high because of this. So, we have to remove this. There can be methods such as capacitive methods, so that the DC can be blocked at the earliest stage. There are some digital methods also which we will cover in later in this course. Now, another limitation is the IQ imbalance. Now, let us have a look at the baseband signal. Basically, when we have designed our signal, it has I and Q component because of its constellation diagram. After pulse shaping, they are not like pulse, basically they becomes continuous, but they still have I and Q components here. The signal which is in the air, it is actually the real part of the x into e to the power j 2 pi f c t, because it cannot have a complex waveform. The complex representation is in the baseband in the mathematics. In real life it only contains the real portion. So, eventually in the air it is xi cos component minus xq sin component. This is the form it is found in the air. Now, this same formulation can be given as formula also, means this x bar here is representing. So, this x bar here is representing xi plus j x q. When you open this expression 2 pi f c t plus j eventually taking the xi component common, we can have similarly by taking our j x q component common, so this together makes twice of cosine 2 pi f c t. This makes sine 2 pi f c t into j. So, this j square will be actually minus 1, so twice of this. So, this is the expression we are getting, and this is the same expression which we were looking for from our RF signal. The only exception is of this twice factor, which is just the amplitude which can be adjusted, but the information is intact in this formula. Now, we have seen this in this formulation because we will see the effect of IQ imbalance. What is this effect? Basically we are supposing whenever we are sending a signal through our any of the architectures, that they are at 90 degree, this is supposed there, right, and both the paths are supposed to have constant magnitude, so that the information level does not change. But in real life it does not happen. It is possible that 90 degree given by one of the oscillator, that phase is not exactly 90 degree, but this is a shift of theta from the 90 degree. Similarly, it is possible that both of the path does not have exact equal amplitude. Let us say this xq is actually having extra alpha times of xq as a gain imbalance. What will happen because of that? If we see we do not have this gain imbalance, even then this theta component, when it will fall on the original y axis, it will have xq cos theta component, which is equivalent to nu xq dash, and xq sin theta component will be added to the actual xi. So, in phase component is also changing. So, it will eventually change its gain. Similarly, even if the phase is 90 degree and the gain imbalance is there, it will change the phase because the vector location will change. So, by assuming that we have both the imbalances, amplitude as well as phase, then we can see that what will be our new I and q signals, which will be read, which will be sent by our modulator, quadrature modulator. So, xi dash, which is the new xi dash, is basically xi plus 1 plus alpha xq sin theta. So, it is a new component in the in phase direction. In quadrature phase direction, we have simply 1 plus alpha xq cos theta. Now, this new xi dash xq dash are the components, are the vectors which will be propagated into the RF domain. So, transmitted signal with the IQ imbalance is given by this formula. Basically what we have done, we have introduced these formulas, these notations in this formulation. So, let us do that. So, our y was xi cos 2 pi f c t minus xq sin 2 pi f c t. But now our xi and xq are not what we used to have. Now they are actually their modified versions. So, let us put these values. Xi is xi plus 1 plus alpha xq sin theta and it will be multiplied with cosine 2 pi f c t minus 1 plus alpha xq cos theta, which is this xq component, new xq component, sin 2 pi f c t. So, let us try to simplify this. Xi component is simply multiplying with the this component, but xq component is little bit more complex, and let us take this common. So, the common components will be sin theta cos 2 pi f c t minus cos theta sin 2 pi f c t. So, it becomes xi cos 2 pi f c t plus 1 plus alpha xq sin a cos b minus cos a sin b. So, it will become now this theta is a phase imbalance and this alpha is representing gain imbalance. So, if you look at this formula and this alpha value can go from 0 to 1 and theta value can go from 0 to 180 degree, but in real life practical scenario it takes very small value and up to 10 degrees has been reported in the transmitter side. In receiver side, because it goes from channel, it becomes very high, the phase rotation can be higher than that, but in the transmitter side normally our oscillators are not so unstable that we will have any phase imbalance more than this. So, these are the imbalances. As you can see here, if we put our theta is equal to 0 and alpha is equal to 0, we will be having our original expression back, and if we put alpha equal to 1, it will be have twice of that one, which will be very high component. So, this was the its expression when we are talking in terms of phase and gain in the polar format. But if we want to talk in terms of the quadrature coefficient, then normally when we want to do this analysis, it is assumed that gain is distributed as 1 plus alpha by 2 and 1 minus alpha by 2 between I and Q branches. So, basically it is not alpha, we will say 1 plus alpha by 2 and it will be having 1 minus alpha by 2. In this way the gain imbalance is still of total alpha. Similarly, theta will not be theta from here, it will be theta by 2 from here, and this vector will also be having theta by 2. By doing this derivation, we can actually see that the output in the time domain, the y, can actually be given as k1 xt plus j k2 x conjugate t. So, again if we see the expression, this y which we were representing in terms of the signal, complex signal and its conjugate, we are doing the same thing, but we are saying that we can attach to constant there, so that we are able to compensate for this imbalances and we can tune this imbalances. So, what is the effect of this imbalances? At the receiver side, how do we get our data in the I and Q domain? Normally, whenever we get our signal, output signal, we multiply with the cosine factor and take its integration over 0 to t and do the low pass filtering. If you do the integration here, the high frequency component, means our y is given by this formulation when there is no imbalance. So, when it is multiplied with your sine and cosine factors, you will have the high frequency component which are basically blocked by your filter, and low pass component is basically xi divided by 2. This 2 factor is again just the amplitude. So, original information xi and xq is preserved. Now, with the IQ imbalance, our I and Q comes out to be what we had seen in our first slide showing the IQ imbalance. So, this is what we will see in the received data. So, there is our information which we will receive will not be accurate. Now, constellation diagram will look something like that. With gain imbalance, there is a gap between these two depending on from where the gain, in which direction the gain is tilting to, and then because of the phase imbalance there is this rotation. So, from here we can see this one is having a negative direction of phase, which we can see from here. So, that this phi, this theta will be negative here. As I have told you that our signal can be shown as xt and x conjugate t, the combination of these two. In the frequency domain, it appears like this in the heterodyne structure. If Fm is our intermediate frequency, which is L over in heterodyne structure, then Fm plus Fc will be having the original signal, but Fc minus Fm will be having the IQ imbalance. This is happening because of this component, which is having the negative frequency conjugate component there. In homodyne case, because our IF Fm is equal to 0, So, our image is actually falling on top of original signal. So, in this case we cannot separate this image by using the filters. So, again heterodyne has this particular benefit in this case. So, to summarize, if we summarize the superheterodyne and homodyne structure based on whatever we have covered till now, superheterodyne is certainly more complex and difficult for chip based implementation. It has why it is, because it has many components and it at every stage it is using filters. Now, depending on the frequency, the filter has a particular size, and if it has to be made tunable, then size becomes increasingly large. Now, for the homodyne case, because there is only one step, one filter will be there particularly for that frequency. So, it is a good candidate for chip based design. In superheterodyne we had seen that IQ imbalance falls in a negative IF frequency. So, by using filter we can remove this IQ imbalance image component and we can have our original component back, it can be avoided. In homodyne the image is falling on top of the signal, we cannot avoid it by using simply RF filters. Alloy leakage and DC offset errors are not that significant, because we can do the 2 level IF conversion by and use the filter again. Alloy leakage and DC offsets, again alloy and RF are at the same frequency, they fall on top of each other, cannot be avoided. It becomes also costly because we have extra component here for the superheterodyne, and for homodyne this design is quite simple. Now, we have seen the pros and cons of these two methods. So, by using the combination of these two methods we can have more better architectures. Thank you.